So far, the only thing we learn is actually this. And then for a simple system, you know, from this step to this step. Okay, so if you go from here to here, you have constant pressure. Then how can you actually rewrite this? So you know, you can write your du equals dq minus p dv. And then you can also write this. Because p is actually a constant, right? It doesn't matter you put it outside or inside your derivative. Then I'm going to move these things to the left. Then have du plus dpv equals dq. And then these things can be written as du plus pv equals to your dq. And we define this as your h is equal to your dq, but this q is not random q. Okay? So the definition of your h is actually u plus pv. What it means is actually when you're under constant pressure, then you measure the heat change. It will give you the change in the enthalpy. Follow this line. We want to talk about this, right? The good definition of your Cp will just simply equals to your partial h, partial t under constant p. So similar to the internal energy is actually good state functions if you express in terms of v and t. For the h, it will be actually a good function of p and t. So u is a good function of v and t. H is a good function of p and t. Since we know this, so you can write a dh. It's going to be equals to partial h, partial t at constant p dt plus partial h, partial p at constant t dp. Then you should recognize the first term of this equation is actually Cp dt plus partial h, partial p at constant t dp. So let's connect this one with du. du is Cv dt plus partial u, partial v at constant t dv. So we say the u is energy, right? Cv dt is heat, so it's also energy. What times v is going to give you the energy term? Yes, the internal pressure. Okay, so P times V give you the energy term. Okay? Using this concept, now you look at the dH. dH is energy term, right? Cp dt that give you heat, Q, is also an energy term. These two terms also need to give you energy term. What times P give you energy? You know, P times V give you energy, right? Right now the P is here. Therefore, this term will be what? It's cool the volume. All right, so now we actually can see that partial h, partial p at constant t. This is related to the excluded volume. So if you actually apply the concept you learned from van der Waals equation, this term is actually related to the B. So remember, when Jules looked at these equations, then he actually started to think about the Joule experiment, right? He wants to actually know how to actually quantify the internal pressure. So in the end, he actually worked on the mu J. Mu J is actually an experiment that you know he did on the constant internal energy. And then he wants to actually measure how the temperature change when he changed the volume of the gas. Joe has an excellent student, Thomson. He actually followed the same thought as his teacher. Okay, then he come to this point. Then he feel like, now I want to figure out the excluded volume. How can I actually determine these things experimentally? So he actually just do the same thing like his teacher. Okay, he say, and now I can transform this equation into partial h, partial t at constant p, partial p, partial t a constant h. So on the top is actually your Cp. At the bottom is actually partial p, partial t, a constant h. Later on we write negative Cp times mu jt, where mu jt is going to equals to partial t, partial p, a constant h. So in other words, if I'm under a constant h condition, if I can figure out how the temperature changes with respect to the pressure change, then I can just figure out what the excluded volume is. How can you actually have constant h? Okay, so now we start thinking about how can I actually have constant h. So remember how joules achieve constant U? We know du is actually dq plus dw, right? What Joule do is actually he used an insulator to surrounding around his system. Therefore, let's actually know heat exchange between the system and the surrounding. Therefore, you know that dq is 0. The other thing you do is actually he actually do the free expansion, and we know free expansion did not do any work, so dw is 0. So that your du is going to equal 0. Therefore, you achieve the constant U condition. Think about now is actually you are Thomson. You want to actually have dH equals to 0. We know dH is U plus PV. How would you actually create conditions that dH equals to 0? I have to say this is actually one of the smartest experiments I've seen so far. To make the U 0 is easy, right? But PV equals to 0, it seems like impossible. What Thomson do is actually he say, okay, I'm going to do an experiment. Initial, final. He actually trying to design a system. You're going to have two pistons. On the left, you have P1. On the right, in the beginning, you have P2. In between, there is a porous film. What this film do is actually allow the gas molecule to pass through if you push hard enough. But important thing is actually you can still maintain the pressure on each side. Actually, in the beginning, I put V1 volume of gas on the left-hand side, and I exert a P1 external pressure. P1 is slightly larger than P2. Eventually, gas will be pushed through to the other side. So at the end will be, you have a P1 on the left, and you have P2 on the right, with the corresponding volume V2. Of course, V2 should be actually slightly larger than your V1 because P is actually small. So that's the initial, that's the final. And he actually isolates his systems. Okay, so what you think is if I can actually find the two pressures, the difference between the two pressures give you the dP. And I want to actually measure the temperature change of the gas after this process. And he claimed this can give you dH equals to 0. Okay, so we need to actually get to see why this actually give you a dH equals to 0. As we say, dH is U plus PV, which we can actually further say, okay, U is actually dQ plus dW plus, okay, dPV. If you actually expand every single terms, okay, your dH is actually equals to these three terms, right? Because you put everything inside adiabatic condition, right? It's all insulated. Your dQ is going to equals to 0. dW, what is dW? dW is actually the work you do, right? So when we know that dW is going to equals to negative P external dV. In the beginning, the work is done by that is actually negative P1 minus the volume change. Volume change is actually going from 0 minus V1. On the other side will be pressure is actually P2, right? Final volume is actually V2 minus 0. For this delta PV, then we know final will be just P2, V2. Initial will be just P1, V1. So this is going to equals to this. This is going to equals to that. So once you have this, then you will realize this is actually P1, V1 minus P2, V2 for your first term. Second term is actually P2, V2 minus P1, V1. And they just all cancels out. So if you design a system like this, you just push the gas from one side to the other. Then you control the pressure difference between two sides. Then you can measure the temperature changes. So by doing this, you can find out what is the excluded volume of the gas. This experiment is actually extremely successful. This experiment later on to have a lot of applications, and one of the most important applications is actually cooling down things. So let's actually how Thomson figure out how to measure the excluded volume experimentally.